Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, maximum points after collecting coins from all the nodes. The problem is a very interesting application of dynamic programming on tree. If you are able to solve these kind of problems on an array, but you face difficulty in solving these problems on trees, this video might help you, because in this video, we'll start the problem from the array version, and then we will see how to convert that problem into a tree version. You should be able to apply this trick in almost all the problems involving trees and dynamic programming, though it might not work where you have to do bottom up, because that process is a bit different. So with that, let's get started. The problem states that you are given a undirected tree rooted at node 0. You are also given all the edges, and you are given a zero indexed array coins, where coins of I indicates the number of coins at vertex I. Along with that, you are given an integer k. Now, starting from root, you have to collect all the coins such that coins at node can only be collected if the coins at its ancestor have already been collected. It means you have to basically collect everything starting from root all the way down to the leaf. Now, if you coins at node I can be collected in following ways. If you collect all the coins, you will get coins I minus k points. If coins I minus k is negative, it means you will lose that many points. Similarly, if second choice that you have is you can collect this many points, like collect all the coins, but you will get this many points. But as a penalty, you have to half the number of coins at each node, which is a subtree of the current node, right? So we have these two choices in which we can collect the coins, collect the points. We have to return the maximum points we can collect after collecting coins from all the tree nodes, right? So let's take an example. Let's say this is the tree 0 1 2. Coins is 844. Basically, at first 0th node there are 8 coins, first node there are 4 coins, second node there are 4 coins. K is 0. It means you can at the first in the first criteria you will be able to collect all the coins which is there in the node, because k is 0, or you will be able to collect coins I by 2 and pay the penalty that you have to reduce everything in the subtree by half. So in this case, because k is 0, it will always make sense to go via first route, because that will give you maximum number of coins. Why will you actually reduce your coins by half by paying some more penalty as well? So that's the best trick here. You will collect all the 8 coins here using the first technique, because k is 0, so you will get all the 8 points. You will collect the 4 coins at 1, because k is 0, you will get all the 4 points, and here as well you will get all the 4 points. So 4 plus 8, which is 16, and 16 is the answer. So hope the problem statement is clear. Now how to solve this? So as always, let's not worry about tree, and let's try to solve a simpler version of the problem first. So the simpler version would look something like this. You have a array, and the problem is exactly similar, but basically you have two choices to collect some points from any index. Either you collect these many points, right, and move forward, or you collect these many coins and reduce everything afterwards to half, right? So basically the same problem but in an array form. Now how to solve this? I would encourage you to pause and try to solve these version by yourself if you know a bit of recursion or dynamic programming. So let's look at the first index. We have to collect all the coins from all the indexes, right? That is clear. So let's look at the first index first. We have 5 coins here. Now how many points we can get? two choices. Either we will get this minus k number of points, or we will get this by 2 number of points, and we have to reduce everything by half. So let's take both the approaches. Let's say we choose to go with the first point collection mechanism for the 0th index. So we will get 5 minus 7, which is minus 2 point here. Basically our point is reduced by 2. Now after this, what we want what is the maximum points I can collect starting from index 1. Isn't this problem exactly similar to the original problem? Original problem states that you are given an array starting from index 0. What is the maximum number of points you can collect? The reduced problem is now saying starting from index 1, what is the maximum number of points you can collect. So hope you can see the recursion here. But this is the first part where we have said that we will reduce we will basically take the points as coins I minus k. The second criteria could be we will collect this many points and pay the penalty. So we will collect k by coins I by 2, which is 5 by 2, which is 2.5, and we have to take floor as well. It is given in the problem, so you have to take the floor as well. So we'll collect 2 points from here, and as a result we will just make everything half. So this is what everything would now be, right? And so on and so forth. Now with this we have to now find what is the maximum number of coins I can collect starting from index 1. So even this problem is exactly similar to the original problem. So hope you can see the recursion here. Whichever path we take, we are actually ending up with the exact same problem. So let's look at it in a bit more detail. So we had this array, the same array, k is 7. So we have two choices for the first index. So we are only caring about the first index. So for first index we have two choices. Either we go via the first route, basically do collect the points as coins I minus k, which is collect minus 2 points, right? And say what is the maximum number of coins I can collect from this array, right? That is first choice. Second choice is collect 2 points, and as a result of collection of 2 points you have to reduce everything by 2 as a penalty. So this 6 become 3, this 8 become 4, this 9 become 4 again because of floor, this 7 become 4, 8 become 4, and so on and so forth. So now you have to find out what is the maximum number of coins you can collect, points you can collect given these coins at each indexes. So in the same fashion you can so this problem, as you can see, is actually the original problem itself. So again you will do the same trick. Basically you will select the first index, see what you can do with the first index. You can either go via the first route, basically collect minus 1 number of points, 6 minus 7, which is minus 1 number of points, and say what is the maximum number of points I can collect from the remaining array, right? And second choice is collect 3 points, basically coins size by 2, and as a penalty reduce everything else by half. So this 8 will now become 4, this 9 become 4, this 7 become 3, this 8 become 4, and so on and so forth, right? So in the same fashion you will again do this problem is also the original problem itself. So again the same trick, you will select the first index, see what you can do with the first index. 2 choices, you will go that 2 choices route. You will keep on doing this until you hit this or this, right? So either you will be hitting, or you will be hitting one, you might be hitting 2 as well. So there is one more choice, which is at 9th index there is 2 as well, right? So one of these 3 you will hit at the end. So from here what you can do, you can again do 2 choices. Either you will take 2 minus k, which is minus 5 points, and once you take minus 5 points you have to now select now give us what is the maximum number of points I can collect from an empty array, right? In the same fashion, if it is if you can actually collect 1 point by making it half, and again say what is the maximum number of points I can collect with an empty array. In the same fashion, if you end up here, you will do the same 2 tricks, and here as well you will do the same. So for the empty array, you already know what is the answer. You know the for empty array you will not be able to collect any more points. So for empty array, answer is always 0. So once you, this is a base case, once you get this, you will keep on you can actually calculate the value of this state. Basically this state value would be max of -5 plus 0 comma 1 plus 0, which is 1. So the maximum points you can collect with in this state is 1. Now once you get the answer for this one, you can move it forward and calculate the answer for the above one, and so on and so forth. Basically the same way recursion will proceed. So hope this entire solution makes sense. Now how would the recursion look like? The recursion is exactly looking like this. We'll have some function f which is giving us what is the maximum point I can collect from this given array. Now from this function we'll call the same function f with the reduced array, and in this case I will be getting a minus k points, right? And otherwise I will be getting a by 2 points, and I will reduce everything by half. So b become b dash, which is b by 2, c become c dash, d become d dash, and so on and so forth. So the pseudo code would be something like this. You will be having a array, right? And as discussed, the base case is when array is empty. So if array is empty, you will return 0, right? And otherwise you will do one of the two things. Either you will take the first route where you will be getting this many number of points, and you will say what is the maximum number of points I can collect from the remaining array, right? Or you can say I will be getting this much number of coins, and I will need to find out what is the maximum number of points I can collect from the reduced array, which is 1 dash will become array 1 by 2, 2 dash will become array 2 by 2, and so on and so forth, right? So this dp array will contain the maximum number of points that you can collect afterwards. Now you have to memorize this as well. Basically there will be scenarios where we have to compute the same array again. How? Let's look at it. So if you just expand this as well, right? So there are two choices. Either you will take 3 minus k, which is minus 4 points, and with minus 4 points, what array you will be getting? You will be getting this same array itself, right? Because the rest of the things will remain same. So see, from this state as well, you need to calculate this. From this path as well, you need to calculate this. So you will be getting same sub problem again and again. So to reduce solving the same sum problem again and again, you can simply do memorization, and that will help you not solve the same problem again. You can simply return the answer from your memory. So what is the overall time complexity now? The overall time complexity is what is the number of state, or how many unique ways this f can be called, multiplied by what you are doing inside each state. So inside each state we are just doing some mathematical operation, max of something comma something. So this is order 1 time, right? How many states we have, or how many unique ways this function can be called? This is how many distinct arrays value can be. So the max size of the array is n, right? So n is the max size of the array. For each element, what will be the value of each of these elements? This element's value can anywhere between 1 and 10 to the power 4, or 0 and 10 to the power 4. So this can be anywhere between 0 and 10 to the power 4. This can be anywhere between 0 and 10 to the power 4. This can be anywhere between 0 and 10 to the power 4, and similarly others as well. So 10 to the power 4 multiplied by 10 to the power 4 multiplied by 10 to the power 4, and so on and so forth. So 10 to the power 4 they will be multiplied n number of times, which is 10 to the power 4 power n, which is nothing but 10 power 4n. So this is the overall time complexity, which will surely not pass because n is 10 to the power 5, and this can only pass up to n equals to 2 at max, right? So we need to optimize this. Now which part? This part is already at its minimal, so we don't need to worry about this. Instead, we have to see if we can somehow optimize this part. In other words, we don't want this array in our state or in our function f, because as if this array comes, this piece will come by default, because we know these are the different like this is the worst case number of states of the array could be, right? This we can reduce this for sure, but with some amortization complexity analysis, but this is the worst case complexity if you have the array. So you don't want this array, but why do you need this array in the first place? Because you have the entire array modified in one of the routes. So if you take this a by 2 route, you have to modify everything afterwards, like b become b by 2, c become c by 2, and so on and so forth. So because everything is modified, that's where you need this entire array, right? But if we need this, if we take this, we will get this and the time complexity as well. So we have to avoid this. In other words, what we are saying is we don't want to modify any of these, but even then we actually want what is the value of b dash, c dash, d dash whenever we reach there, right? So in other words, what we are saying is we don't want to make it 3, 4, 4 and other things. Instead we will keep it this itself 6, 8, 9, 7, but whenever we reach this state or whenever we want to compute the value here, we should be able to recompute whatever is the what is the final value here. Instead of 6, we should be able to get 3 somehow. So this is a very very popular trick wherein you will defer your computation and maintain enough things so that you can actually compute the value afterwards, right? So in this case, we don't want to actually calculate everything, but we want enough information with us so that we can compute everything. Now what is the information we want? The only information we need to keep with us is what is the how many 2's we need to divide it by, because every time what is the value of array of I at any given point. Array of I at any given point would be divide by 2, this entire thing divide by 2, this entire thing divide by 2, and so on and so forth. So basically at any point, if you are able to somehow keep track of how many 2's you have divided this divided everything after I by, then you should be able to recompute the value at that moment itself, right? So let's look at it one more time. So instead of the entire array now, what we just have two things with us: the first index and how many 2's we need to divide it by, right? Not it, basically how many 2's we need to divide everything after this index, right? So initially we don't need to divide anything, so it is 0. Basically we don't need to divide anything by 2. So at this state, what is the value of array of index 0? It will be 5 divided by this many number of 2's, but here there are 0 2's, so the value will be 5. Now we know, once we know the value, we can do our job. Basically either it would be array I minus k number of points, or array I by 2 number of points taking its floor. So either minus 2 points or 2 points. Now once you have this minus 2 and 2, what you can actually do, while going to the next state, you can actually maintain the same thing. How many 2's I need to divide it by? So here you don't need to divide it by anything, so you just maintain a 0. So what is the value, what is the exact value of 6 here? The exact value of 6 is 6 by number of times I need to divide it by 2, 0. So exact value is still 6. So I can take this 6, move forward. 6 minus 7 is the one state. and 6 by 2 is another state. And once you go with 6 minus 7, you don't need to do anything afterwards. So this is still f of 2 of 0. Basically, give me the maximum number of points I can collect starting from index 2, given that I don't need to divide anything by 2. But if you go by this route, you are saying that you have to pay the penalty of dividing everything by 2. So now you are saying give me the maximum number of points starting at index 2, but this time I need to divide everything by 2. So here when you come, the value at index 2 was 8. So just forget about this array. This array doesn't no longer is required. You just look at the exact value here. Exact value is 8. So value at index 2 is 8, but it says that you have to divide everything by 2 as well. So you will divide it by 2, you will get 4, and see, this was the exact value. So you can actually compute what will be the value with just this state in your recursion. You can just keep track of how many 2's you need to divide it by. In the same fashion, if you have gone this route, it means you will have divided this by 2 with the penalty of dividing everything else by 2. So you will say what is the maximum number of points you can collect starting at index 1, given you have to divide everything by 2 once. So hope you understand what we are trying to do here. So the pseudocode would simply be modified like this. So instead of this array now, this array is now fully constant. We are not touching this array at all. Instead, we are actually deriving the actual value inside this function itself. So we keep maintaining how many times we have to divide it by 2. Now inside this function, the first thing we do is actually calculate the value, because array of index is not the real value. The real value is something you will get by dividing it by 2. Now notice that this operation is not equals to v by 2 power n. They are completely different. So just keep that in mind, because of this floor thing, like you are taking this floor here by default. So once you have the actual value here, you can do the exact same thing. You can say I have two choices, either I will take val minus k or I will do val by 2. If I do val minus k, I don't need to pay any extra penalty. Everything after me will stay as it is, and what everything after me will be, this will be divided by this many number of 2's. So index plus 1 divided by this many number of 2's. Similarly, for the other case where you are dividing it by 2, you have to pay the penalty of actually dividing everything else by 2. So you are saying everything else will now be divided by how many times I am divided by 2 plus 1, right? So this is the overall algorithm now. What is the time complexity of this algorithm now? Again, the same thing, number of states multiplied by how many times what we are doing inside each of these state. So what we are doing inside of each of these state, it is basically a loop that runs over by 2 times. So whatever is the maximum value of by 2, that we are doing inside each of these state. So let's represent this by b. B is the maximum value of by 2. Now how many different set of values you can call this with? Again, you have done memorization here so that you don't need to compute same thing again and again. So how many distinct value of these could be? Number of distinct value of index could be n, and number of distinct value of this by 2, let's say is b, right? Maximum value of by 2 is b. So n into b is here. So overall time complexity is nb square, right? Now n we know it is 10 to the power 5, but what is the value of b? B is representing the maximum value of by 2. Now what the maximum value of by 2 can be? I would encourage you to pause and try to think about this for few minutes. So hope you thought about it. The maximum value of b here would be number of times you can actually divide it by 2 to make it 0, because after 0, no matter what you divide it by, everything will be 0, everything will remain 0. So let's say after a state you reach some array where everything is 0. Now dividing it by 2 doesn't make sense much, right? Because even if you divide it by 2, you will get 0 only. So if everything is 0, the maximum sum you can get is actually 0, right? So that's the basic thing you can do. You have to make sure how many times I have to divide the maximum value here. Maximum value is 10 to the power 4. How many times I can divide 10 to the power 4 by 2 so that it becomes 0 at the end. So you can see it is log n number of times. So basically the value of b would be log of 10 to the power 4, log base 2 of 10 to the power 4, which is approximately 14. So if you divide it by 14, if you divide it 14 number of times with 2, it will become 0 at the end. And if it is 0, you don't need to go further, and you can simply say the maximum point I can get is actually 0, because everything else will be 0 after this state, right? So maximum value of b here is 14, and to actually keep this here, you can simply add one more criteria here. You can say if by 2 is greater than 14, you will return either minus infinity, or you can say it is 0. Anything will work. So you have to add just one more criteria here to actually make it restrictive to only 14. So now the value of maximum value of b is 14. So 14 square multiplied by 10 to the power 5, which is well under 1 second. So this will pass the given time constraint of the problem. But everything till now we have solved on an array. The original problem states that you are given a tree and you have to calculate the maximum points you can collect on that tree itself. So the actual problem was something like this. You are given a tree, each tree has some coins. You have to collect the coins. Two choices: either you can collect coins minus k number of points, or you can collect coins by 2 number of points, with a penalty that you have to divide everything beneath it by 2, right? So if you are collecting, let's say, coins by 2 points here, so you are collecting 4 points here, then you have to reduce everything here by 2 and everything here by 2, basically everything in the subtree by 2, right? So this will become 3, this will become 1, this will become 0, this will become 45, this will become 2, this will become 1. So that's what the actual problem was. Now how to solve this? So think about this. This is also exactly recursion, right? So at this stage you have two choices. Either you can take 2 minus k number of points, let's say simplicity k is 2 here, so either you can take 2 minus 2, which is 0 number of points. If you take 0 number of points, what you want what is the maximum number of coins I can collect with this in this subtree, maximum number of coins I can collect, maximum number of points I can collect in this subtree, maximum number of points I can collect in this subtree, maximum number of points I can collect in this subtree, right? So each of these are exactly the same problem, which is I want to collect the maximum number of coins in a particular tree. It's just that the tree is now a bit smaller. Similarly, second choice could be, with this you collected the second you moved the second path, which is collecting collecting coins I by 2 number of points. So you collect 1 point here. Now you have to pay the penalty of reducing everything by 2. So again, instead of actually reducing, you will hallucinate and say I will keep the state how many times I have to divide it by 2. So I will just say what is the maximum number of points I can collect in this subtree, given that I have to divide everything by 2 one number of times. How many points I can collect in this subtree, maximum point I can collect in this subtree if I have to divide everything by 2 one time. How many points I can collect in this subtree if I have to divide everything by 2 one time. And similarly, how many points I can collect in this subtree or in this tree given everything is divided by 2 one number of times. So this is exactly what we have solved previously. Hope you can see the recursion here as well. So the same solution, you can actually transform it in this tree fashion. So what you can say, I will simply find out the value here with by 2 here. So instead of index, we now have a root, right? Now once we have the value, we have two choices. Either we can do collect by two number of coins, divide by two number of coins, number of points, or we can collect coins minus k number of points. So this is the actual value of coin in the current node. So either you can collect these many number of points, or you can collect these many number of points. Now if you collect these many number of points, you have to go to every child, and for every child you will ask what is the maximum number of points I can collect starting from this particular route, and I have to divide everything by 2 these many number of times, because I have, as a penalty, I have to divide it one more time. So I am adding one more here, right? In the second choice, again you will do the same thing. You will go to each of the route and ask for how many what is the maximum number of points I can collect starting from this particular route, given I have to divide everything by 2 the same number of times, right? Now with by 2 you get the maximum value you can collect. With minus k you get the maximum value, maximum point you can get. So the actual answer would simply be max of these two, and you return that as an answer, right? Exactly the same thing, just you just don't have one single sub problem. Instead you have n number of sub problems given the number of childs you have for the given particular route, right? So what is the time complexity of this solution now? So if you look at naively, this will look like, okay, how many number of states, or again one more thing, you actually have to memorize it as well, because of the same reason. You might have to compute the same state again and again, so memorization is important here as well, right? So with memorization, what is the complexity? Number of states multiplied by what we are doing inside each state. So number of state is simply root into by 2, which is number of different value of root could be n, and by 2 the maximum value we already looked at, it is b, right? This is the number of states you have. What you are doing inside each of these state, you actually go over all the value from 1 to this by 2, which is b, maximum value. And after this, what you are doing, you are iterating over all the childs 2 times, right? So basically 2 into number of child that you have. Now if you look at this complexity in a very brute manner, number of child, you can say in worst case can be order n. So the tree could be something like this, like all the children are attached to the same root node. So maximum number of child that you can have is order n. So what you can say, the complexity is nb into b plus n, which is order n square b roughly, which will not pass the given time constraint for sure, because n square will be 10 power 5 square, right? But if you actually look at it closely and try to find the amortized time complexity of this expression, this will actually come as the exact same thing, which is n into b square. So I would strongly encourage you to pause and try to actually derive the amortized time complexity by yourself. We have done this multiple times in this channel in the past, so if you are following, you should be able to derive it by yourself. So this is how you will derive. So this is what our pseudo code was. Now notice what is the time complexity. Time complexity would simply be how many iterations I am doing in this state, how many iteration I am doing in this state, how many iteration I am doing in this state, and so on and so forth until n comma 1. Similarly, all the way for 2, the same thing for 3, same thing for 14, because by 2 can at max be 14. Now what we are doing inside this state, in this what we are doing, we are iterating over val, right? So basically we are iterating this many number of times plus number of child of this node, right? So that's what we are doing. We are iterating over 1 and number of child of 1. Similarly for this sorry, this will be, yeah, so this is again we are iterating for 1 because here, and then number of child of 2. Similarly for this, 1 and then child of 3, 1 and then child of n. In the same fashion for this one, what you will do, the by 2 is 2, so this loop will go 2 times, so you will do 2 iterations here, and then child of 1, then child of 2, child of 3, other child of 1, and so on and so forth. Now if you look at this first one itself, just take out this first one completely. So if you take out this first one, this will be n into 1, right? So that's fine, plus summation of children, right? In the similar fashion, this will be n into 2 plus summation of children, n into 3 plus summation of children, and then n into 14 finally, or n into b finally, plus summation of children. Now this part is n into b square, right? Because n into 1 plus 2 plus all the way up to b, which is b square. So this part in itself is nb square. What about this part? This is sum of children b number of times. So this is sum of children multiplied by b, right? What is sum of children here? Sum of children is how many times you, like how many children's an overall tree can have. There are n nodes in total, so if you sum up all the edges, you will be getting 2n at max. So this is the overall value of summation of children, or summation of edges, if I put it correctly, summation of edges. So 2n into b, so nb square plus n into b, which is equals to nb square itself, right? So this is sufficient to pass the given time constraint. It is not actually n square b, but rather nb square. So hope this entire time complexity analysis makes sense. If you have watched this point, I would strongly encourage you to pause and try to code this entire thing by yourself, because that's the point where you will understand what is involved in the problem, and you will be able to retain this for a longer time and apply this in the future context as well. So next we're looking at the code. The code is exactly what we have discussed in the pseudo code. We just have this memoization array with us, dp, and then we are building this adjacency list from the given edges. After that, I just called max point of 0 0 minus 1. So this 0 denotes the root, this 0 denotes the number of times I have to divide it by 2, and this minus 1 denotes the parent. Now you might think, okay, why parent is there, and if parent is there, why not parent is involved in this dp array? So that's a very good problem, very good question, and the answer is parent is deterministic. So in dp array you only put those things which is non-deterministic, but parent is always deterministic for a given root. For a given root you can actually find out the parent. So instead of actually doing this directly, what you could have done is, the given tree is already rooted at 0. So with 0 you can actually find out what is the parent of every node, because you already have given a root. So for every node you can find out the parent. So instead of taking the parent, then you can just simply do int parent equals to whatever the value, whatever the array you have stored the parent in, parent of root. So this parent is actually derivable from root, and because that's the case, you don't need to put this inside this dp array, right? Even though it is a part of the recursion, right? So you can just try to iterate it, do it a couple of times, and you will see what exactly I'm trying to say if you don't understand it, or you can just post it in the comment section if you feel difficulty in any piece understanding why parent is still not there, why parent is still there. So this parent just denotes what is the immediate parent, so that in adjacency list we don't iterate over the parent. That's the only thing, there nothing else is there. So if I is parent will continue, otherwise with by 2, I will simply do max points of I comma by 2 plus 1 and then root. In the same fashion with minus k, val minus k and then I and then simply by 2, and the parent now become root. Once we have these two value, we can simply do a max, and that will be assigned to the answer as well, so that it will be going back to this DP array because we have taken it as a reference. So hope this entire solution makes sense. If you have any doubts in any of the fees, feel free to follow up in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already, and I will see you in the next one. Thank you.